Truth tables. Logic problems, sometimes called brain teasers, can appear difficult to solve for many people. Let's examine the problem of the knight and knave, which has long been the inspiration for many other problems with a seemingly impossible choice. The problem is this: knights always tell the truth and knaves always lie. On a path, you encounter both. The first says to you, "We are both knaves." How can you determine who is the knight and who is the knave? The question seems impossible. However, in reality, it is a simple binary problem. Truth tables help us perform logical operations between inputs to show a final output. They determine the truth value of an argument. In the case of our knight and knave, let's examine all the possibilities below. The table shows any outcome of the first and second person lying. The statement made is "we are both knaves." If the first person is telling the truth, that would make the first and second person knaves, regardless of whether the second person is telling the truth or not. If the first person is lying, he can't be a knight because knights don't lie. Since he is a knave, that would make the second person a knight. By looking at the truth tables, we can see which line the false matches up with a knave and the true matches up with a knight. Therefore, we can draw the conclusion that the first person is the knave and the second person is the knight. Truth tables are very useful in solving logical operations. The most common operations are and, or, and not. And is the logic operation where given two binary inputs, P and Q, both need to be true for the output to be true. And this little caret here symbolizes and. So if P is true and Q is true, then the result is true. However, if P is true and Q is false, then the output is false. If P is false, but Q is true, the output is still false. If both are false, the output is false. So both of them need to be true in order for and to be true. Or is the logic operation where given two binary inputs, P and Q, only one or the other need to be true for the output to be true. And here the symbol is a V, or an upside down caret symbol. If either one of these is true, the output is true. So if they're both true, the output is true. If one is true and the other is false, the output's still true. Same if you switch them. However, if both are false, the output is false. Not is the logic operation for negation, where given a binary input P, the opposite is the result. So we have a little tilde here as our symbol to mean not P. So if P is true, not P is false. If P is false, not P is true.